a non-empty subset W of a vector space V is called a subspace of V if W is itself a vector space under the operations of addition and scalar multiplication defined on V. Let's go back and think. Now, in order to be a vector space, V has to have vector addition and scalar multiplication defined on it, and it has to satisfy the 10 properties. Now, if we have a non-empty subset W of V, so V is contained within, W is contained within V, W is a subset of V, then W is, now if W is itself a vector space under the same operations of addition and scalar multiplication defined on V, then we call V, then W is a subspace of V. So W has to be a subset of V. W has to be a vector space under the same operations defined on V. And if that happens, we say that W is a subspace of V. Now, before continuing, let's recall the 10 conditions to be a vector space. It must be closed under addition. Addition must be commutative. We must have the associative property of addition. There must be a zero element so that U plus the zero vector is U. There must be the additive inverse vector so that U plus the additive inverse of U is the zero vector. We must have closure under scalar multiplication. Scalar multiplication must be distributive over vector addition. We also must have distributive property over scalar addition. We must be able to have the associative property of scalar multiplication. And we must have the scalar 1 so that 1 times U is U. So you must satisfy those 10 properties. So for W to be a subspace, it has to satisfy the 10 properties using the same operations defined on V. And of course, W would have to start being a subset of V. Now let's think about it for a few minutes. If W is a subset of V, then that means all the vectors in W are in V, so that most of the properties are already true. The commutative property of addition is true because U plus V is equal to V plus U for any vectors in V. Well, the vectors in W are in V, so therefore it must be true for the vectors in W. So that's okay. The associative property of addition must hold for all vectors in V. Well, all the vectors in W are also in V, so it must hold for all the vectors in W. Well, the same zero vector for V must work for W because there's only one. U plus opposite of U, this must be satisfied. Scalar multiplication is distributive over vector addition for all vectors in V. Well, all the vectors in W are part of V, so in particular it must be satisfied for all vectors in W. Likewise, likewise, likewise. Now there's only 2 properties that we have to worry about. Now remember, U plus V would be in W, but all this says is that U plus V is in V. It doesn't say that they will remain in W, so we've got to check that one, and we've got to check closure with scalar multiplication. So we must check 2 of the properties. I'll put that in writing for you. Test for subspace W. So to find out if W is a subspace of V, we really only have to test 3 things. First of all, we need to make sure that W is non-empty. In other words, it's got to contain something. 2, we've got to show closure of scalar addition. If U and V are in W, then U plus V must be in W. And we've got to show closure for scalar multiplication. If U is in W and C is any scalar, then CU is in W. So that's really all we need to do to test to determine whether a set W is a subspace of V. Now remember, W must be a subset of V. So if W is a subset of V, we're trying to find if W is a subspace of V. We only have to check these 3 conditions. Show that the set W is equal to the set of all ordered triples x, y, 2x minus 3y for x and y real numbers is the subspace of R cubed. Well, obviously W would be a subset of R cubed because R cubed would consist of ordered triples. W consists of ordered triples, so W is obviously a subset of R cubed. In order to show that W is a subspace of R cubed, we must show that it fits the 3 conditions. First of all, we've got to show that W is not empty. Well, to show that W is not empty, I've got to find one element that would be in W. Well, to do that, I'm going to just choose the very easiest x and y's I can come up with. I'm going to x be 1 and y be 1. So if x is 1 and y is 1, then 2x minus 3y would be negative 1. So we would have 1, 1, negative 1 is in W. So there is an ordered triple in R cubed that satisfies the requirements of W. X, y, 2x minus 3y. So W is not empty. Now we've got to show that W is closed with respect to vector addition. So if I pick 2 vectors in W, I've got to show that my answer would be in W. Well, let's let A, B, C, and D be real numbers. Then we'll let U be AB, 2A minus 3B. See, this satisfies the pattern XY, 2X minus 3Y. I'm just letting A, B, C, D be such that AB is A and B and 2A minus 3B. And we'll define V to be CD, 2C minus 3D. So U and V are both obviously in W because they satisfy the pattern. Now U plus V is going to be vector AB, AB, 2A minus 3B, CD, 2C minus 3D added together. So that would be the vectors U plus V. Now we simply do the vector addition by adding the like components. So, adding the first components, A plus C, B plus D, 2A plus 2C minus 3B minus 3D. I just added the first components, added the second components, added the third components. Well, this satisfies the pattern of A plus C, B plus D. Now I can factor 2 out of this, 2A plus C. Factor a 3 here, a negative 3, B plus D. So we see it satisfies the pattern of X, Y, 2X minus 3Y. And if we let X be A plus C and Y be plus B plus D. So it's X, Y, 2X minus 3Y. satisfies the pattern, so therefore U plus V is in W. Now we've got to show that scalar multiplication is closed. So we'll let C be a scalar, and let's consider CU. CU would be C times AB 2A minus 3B, which is CA, CB, 2CA minus 3CB. Well, simply multiply through by the scalar. Therefore, CU is in W, because I just let CA be X and CB be Y, so I have X, Y, 2X minus 3Y. So if we satisfy all three conditions, I know that W is the subspace of V. So to prove that W is the subspace of V, I simply need to show that W is non-empty, that scalar addition is closed, that vector addition is closed, and that scalar multiplication is closed. And of course, W does have to be a subset of V. To determine whether A, B, 4, such that A and B are real numbers, along with the standard operations, is the subspace of R cubed. Well, now obviously it's going to be a subset. If we let this be S, obviously S is going to be a subset of R cubed, because R cubed would be the set of all possible ordered triples, and here we have A, B, 4. So, and A and B are real numbers. So it's obviously S is a subset of R cubed. So first we need to show that S is not empty. Well, 1, 1, 4 is an element of S. So I find an element in there. 1, 1, 4 is in S, so it's not empty. 2, we will examine closure of vector addition. Well, if I pick, let's let U be the vector AB4, and let V be the vector CD4, then U plus V is going to be A, B4 plus C, D4, which is A plus C, B plus D, 8. But it doesn't satisfy closure because all these had to have 4 as the third component. I added 2 vectors in W, so obviously U is in W, V is in W, so I added 2 vectors in W, and I got a vector that was not in W. So therefore, not closed, therefore not a subspace.